Okay, so today we're covering two chapters. Okay, we're covering chapter 12 on EM waves. Then we'll be covering the chapter on sound. So chapter 12 and chapter 13 of the textbook. So let's start off with chapter 12. So for chapter 12, we're going to cover this idea of EM waves. Okay, so let's start off by the basics of what are EM waves. So EM waves are actually all around us. Okay, all around us. And many things that we are using actually consist of EM waves. So what are the EM waves? Okay, you need to know the order. So take a look here. So I'm going to start over here. Okay, I guess some of you have already have a method of memorizing the order of the EM wave, but in case you do not have, okay, so the EM wave, the order is as such. Okay, so it can be rugby match is very unlikely xylophone game. Okay, so whatever the thing is, so you can go accordingly. But what's important in terms of the order? First thing, you need to know in terms of wavelength and frequency. So radio waves, okay, so radio waves, microwave, infrared radiation, visible light, ultraviolet ray, X-rays, gamma rays. So this is the order. Now, why is it in this order? So radio wave has the longest wavelength. So longest wavelength. So in our previous chapter, we learned that wavelength is lambda, while gamma ray actually has the shortest wavelength. Okay? So we know that from gamma ray to radio waves, in increasing order, it's like this. Now, so radio wave has the longest wavelength, gamma ray has the shortest. The other thing you need to know in terms of the order, why must it be in this order? It's not just about the wavelength, but also in terms of the frequency. So gamma ray has the highest frequency. Okay, so while radio wave actually has the lowest frequency. So this one, the order is the other way around. So lowest is radio wave, highest is actually gamma ray. So this is the idea that you memorize. All these little numbers, do you remember? The answer is no. The only one that you need to remember is this, about X-ray. Okay, X-ray, the wavelength is about 10 to the power minus 10 meters. This is also the same as the size of an atom. So this one has come up before, so I just need you to just take note of this. Okay, that X-ray is actually equivalent to the size of an atom. Okay, the wavelength is equivalent to the size of an atom. So first up, the order. Second thing, you need to know which one is the shortest wavelength, which one is the longest. Next one, you know which is the lowest frequency, which is the highest frequency. So this is the order in terms of the EM wave. Okay, now, but the thing is this. So what exactly are EM waves? So now we're going to cover in terms of the properties of them. Okay, so the order is one. The properties is the other. I'd like to highlight one part here before we go on to the properties. Is actually this thing over here. Okay, the frequency of an electromagnetic wave is related to its energy. So the highest frequency, the highest energy. This actually can help you to remember, okay, the order. Why do I say so? It's really because gamma ray is on one end of the spectrum. We know that this is a light ray. This is an EM wave that is very dangerous because it has it can kill people. Why is it able to kill people? Because it is highest frequency, which means that it will actually has the highest energy level. Okay, so if it has the highest energy level, imagine such high energy beam shoots at you. Obviously, you're gonna have its effect. Okay, you're gonna feel its effect. Okay, so this part here, just take note of it. Okay, next, in terms of property of EM waves, there's quite a few. So let's go through all of them. So first, EM waves are transverse wave. They comprise. Okay, so first thing, they are transverse wave. They comprise of electric and magnetic fields that oscillate at 90 degrees to each other. So think of it 3D. So you can see here the electric field is this red color region. So I'm just going to draw it using red color line. This is along the horizontal axis. Okay, the electric field. Okay, so the horizontal axis is the electric field. So this is going along this way, left and right, whereas the magnetic field is actually going up and down. So this is what they mean by they are oscillating 90 degrees to each other, because one is going left and right, the other one is going up and down. Okay, so do take note of this in terms of the what electromagnetic waves are. Second one is electromagnetic waves can travel through vacuum. Okay, so they do not require a medium to travel from one point to another, which also means that they can travel through vacuum. So point 2 is important. Okay, sorry, let me use red color to just show this. Point 3, they transfer energy from one place to another. This is a general wave property. Okay, so this has been covered before, that wave actually transfers energy from one place to another. Okay, next thing, special to EM waves, they travel at the same speed of 3 times 10 or 8 meters per second in vacuum. So take note, the word in vacuum is important. Now, what do they mean by they travel at the same speed of 3.0 times 10 or 8 meters per second? So let's go back to the waves. Now, so what they're trying to say is radio waves, microwave, infrared radiation, visible light, ultraviolet, X-ray, gamma ray, all of them, when they are in vacuum, they all travel at 3 times 10 to the power of 8 meters per second. So this is also equivalent to 300 million meters per second. Okay, so all of them travel at the same speed because they are all EM waves. Okay, so they travel at 3 times 10 to the power of 8 meters per second in vacuum. Next one, the wave speed equation, V equals F lambda, is applicable to all. So do take note, EM wave chapter, you need to apply V equals F lambda to the calculations. Okay, next thing, it travels, when it travels from one medium to another, the speed and wavelength change, the frequency does not, because the frequency depends only on the source of the wave. So this one, do read up a little bit more. I actually covered this in the chapter of wave itself, but I think this one, an additional explanation would be good. Okay, so do read up a little bit on it. Okay, so I should put star. So we'll read up a little bit on it. Right? They obey the laws of reflection and refraction. They carry no electric charge. So this too is the other two properties. Now, if you ask me what are the properties that you should try to remember for EM wave that's unique to it, it's actually those two that I've drawn in stars. Okay, the third one, okay, that's quite unique to it is this. I use the word quite because transverse wave, quite a few waves are transverse waves, so it's not unique. Okay, however, this part in green here, okay, is the unique part, right? Because it tells you what exactly EM waves are. So those in the star, if you ask me, are the 3 properties you should try to remember when you hit for the exam, right? Because these are unique to EM waves, and whenever they ask you for the properties of EM wave, you should be quoting these 3. Okay, next, let's go on. Okay, so these are some examples. Do take a look through, right? Because really calculations are still part and parcel of it. Okay, so all these prefixes comes in, so you just have to be familiar with it and be used to it. Okay, so actually what do we go through? We actually go through the whole EM wave spectrum in order of frequency. So radio waves, lowest frequency, longest wavelength, all the way to gamma ray. Okay, so this is actually gamma ray, highest frequency, shortest wavelength. So the order is important, so do take some effort to memorize them. Second thing is, EM wave have common properties. So all of them have common properties, and this is listed in table 12.1. I put a star for 3 of them, for 3 properties. So those are the ones that I need to pay a bit more attention to. Okay, so we've covered this 2 in 12.1. Okay, 12.2, application. Now, in EM wave, the application is important. Okay, you should know what are they used for. So radio waves total got 3 main functions, or three main applications. So first one, radio. So obviously radio use radio waves, that's why they call radio. The other one is called over-the-air television. So this is the one where the old TVs uses the antenna. Okay, yeah, so that's the over-the-air television. And communications, so your walkie-talkie and stuff. Okay, so communications. Now generally 1 and 2 are the ones you should try to remember. Okay, I put 1, 2, 3 because that's the order that normally I will state when it comes to the application if they ask for it. Okay, so next one. I won't go through the details here because seldom is the details are being asked. Okay, but it's a good read in terms of what it does. Oh yes, I'd like to highlight one part for radio comms because this has come up before. Okay, do take note. If you want good reception for radio comms, or you want good reception for radio comms, it's better to use shorter wavelength. Okay. Okay. Sorry, for good reception for radio waves, and if you are using a shorter wavelength, it should be unobstructed straight path between the transmitter and the receiver. So generally, what you realize is that for the antennas, there is always placed at the top of the roof, and they try to make sure that there's nothing around it that's obstructing the wave from reaching it. Okay, so generally, if you want a good reception, it should be unobstructed, and it should be a straight path between the transmitter and the receiver. So I repeat again, if you want good reception, do take note. Okay, the radio waves of shorter wavelength needs unobstructed straight path between the transmitter and the receiver. So this is a bit of an additional point. You got a bit of bandwidth to remember this. Okay, do take note of it. Next, microwaves. What are they used for? Obviously, first one, microwave oven. Now, this one here is satellite TV. So any satellite communications, even GPS also uses satellites. So anything that deals with satellites are generally done by microwaves. So I like to take note, there's a difference between satellite TV and over-the-air TV. They are different things. So if you see over-the-air television, radio waves. If you see satellite televisions, generally you put microwaves. So do take note of that. Okay, so that's the application of microwaves. Now, infrared radiation, this is the one that typically we have in our thermometer and our remote control. So remote controls for TVs and air cons and stuff generally uses infrared radiation. Your ear thermometer, or actually now we have the forehead thermometer, okay, or we call it the infrared thermometers. This is also infrared thermometer. This is also where the application of infrared radiation comes from. And the next one, intruder alarms. So they actually uses motion sensor. Okay, so infrared radiation is used as a way to detect motion to activate the intruder alarms. Okay, so those are the few. Now, visible light, one simple application, optical fiber. Okay, so this will allow us to see. So telecoms, when we talk about fiber in our homes and stuff, actually we are looking at optical fibers. Medical purposes, okay, so scopes. Okay, you can go and search out on more on medical scopes. Well, scopes actually uses the idea of optical fibers. Okay. Now, UV radiation, sunbathe is one. Sterilization of equipment, another one. So sterilization of equipment is to kill the bacteria and stuff. X-ray. Okay, first is radiation therapy, radiation imaging. So a lot of people like to put, like, you know, what's the application of X-ray? You can write X-ray. So the idea is you're not so write the word X-ray for its application. X-ray is just a short term that we use quite readily around hospitals that we know. But in general, the X-ray that we take is actually called radiation imaging. Okay, so X-ray is used for radiation imaging. Okay, or the other one is radiation therapy. So what is radiation therapy? Is sort of like using X-rays to go and kill the cancer cells. Okay, kill the cancer cells. Last one, gamma ray is used for radiation therapy once again. Okay, sometimes you'll use the word very precise to kill cancer cells, because gamma rays are very strong in terms of energy, so it will kill the cells. So if I'm able to direct the gamma rays to the point where the tumor or the cancer is, it's able to destroy the cells over there. Okay, so it's actually quite commonly used, okay, to ensure that the tumors are killed. Okay, all these things, do you remember? Answer is no. Okay, don't need to remember all these details here. Okay, but it's a good read, especially if you're interested to go into the medical line. Okay, so in summary, okay, all these questions for you to try. In summary, this is what you need to remember. Okay, so all the applications are summarized here. So if you are lazy to read through all those things at the top, these key ideas here will be good enough. So what we know, what we have done so far, okay, first thing, we have learned about EM wave and categorize them, arrange them in order of wavelength or frequency. Okay, so your idea of radio wave, microwave, infrared radiation, visible light, ultraviolet, X-ray, gamma ray, you need to remember the whole sequence. So that's why we did when we go through them. Then we went through what are the common properties between all these waves. So we said they are transverse wave, important. They do not need a medium to propagate or to travel. This means that can travel in vacuum. Okay. And next, it travels at 3 times about 8 meters per second in vacuum. So these three are the key ones that you should try to remember. In terms of application, okay, we just went through. So this is all of it. So EM wave is a relatively short chapter. That's quite easy to remember. Okay, and if it comes out, actually, if you ask me, this is one of the chapters where you should get your marks from. Okay, if it comes out in the exam. Okay. Now, so that's for EM waves. So I'm gonna stop there now. So for this for EM wave, we are done. Next, we're gonna go into sound. Okay, so EM waves is a transverse wave. It's called the electromagnetic wave. Now we go on to sound. Now do take note, sound and EM wave, why is the chapters back to back? It's really because we are looking at transverse wave and transverse waves and longitudinal waves and comparing them. So sound is a longitudinal wave. Okay, in your syllabus, as I mentioned before to many of you, sound is sort of like the only one longitudinal wave that you have picked up. Okay, now, so let's go jump into it now. So sound. Okay, so what is sound? 13.1. We're going to learn how sound is generated by vibration. We're going to learn how to describe the mechanism in which sound travels. So sound is a form of energy that's transferred from one point to another. So this is just in general describing waves. However, the important part is that sound is a longitudinal wave. Okay, so take note, sound is a longitudinal wave. Okay, so what are longitudinal waves? It is where the wave travels parallel to the direction of vibration of a medium. And this was what we covered in chapter 11. Okay, so this is just a recap a little bit from 11 and coming to chapter 13. So one of the questions in Express they like to commonly ask, how is sound produced, or how does a sound from a speaker, okay, maybe this is a speaker, how does the sound from a speaker reaches our ear? Okay, sorry for the ugly ear. How does the sound reach our ear? So this is quite you do see it coming out quite a fair bit here and there. So that's why I'll take some time to go through this. So first thing, okay, how is sound produced? So generally it starts off with an object vibrating in air. Okay, because sound normally, the sound that we hear normally is because of the air particles vibrating. So the object vibrating in air, okay, causes the layer of air particles around it to be displaced. So first thing, object vibrate. Next thing, cause the layers of air particles around it to be displaced. Okay, now, so I'm showing you the general sequence. So once you know that the layer of air around it is being displaced, next thing, okay, you also say that okay, so the layers of air particles around it to be displaced. These air particles displaces the surrounding air particles. Okay, so sort of like saying the object hit the air hit the air. So, can I say again? The object hit the air or collide with, or causes the air around it to vibrate. Then the air that's vibrating more vigorously collides into the surrounding air, okay, and cause them to also vibrate more vigorously. So it's sort of like a chain reaction that we are seeing. So what happens is that object vibrating in air causes air around it to be displaced. These air particles displace the surrounding air particles. Okay, this process continues. Okay, this process continues to produce and produces, okay, and produces a series of compression and rarefaction. Okay, allowing air to travel, allowing sound to travel as a longitudinal wave. Now, so this description here is sort of like quite a complete description in terms of how sound travels. Okay, but which are the main points that you should write whenever they talk about asking you to describe how sound travels, right? Two of the main points that you should have all the time is this and this. Because of the idea of longitudinal wave, because of the idea of compression and rarefaction. Now, point 1, 2, 3 is sort of like the how it works in the particle level. Okay, so that's why 1, 2, 3 is also equally important. But when we talk about the bigger idea, it's actually point 4 and point 5. So, question that people ask is just, so do I need to write everything if they ever ask me to describe how sound travel? My suggestion is just write everything lah. Okay, just write everything. Okay, no need to worry too much. Just write. Okay, so how sound travel is very described on top. So the question is, you talk about compression and rarefaction. What is really compression and rarefaction? So this is the idea here, compression and rarefaction. So compressions are regions where air pressure is higher than the surrounding air pressure. Rarefactions, okay, are regions where air pressure is lower than the surrounding air pressure. So if you look at the diagram here, you can see that rarefaction here is more spread out. And because it's more spread out, obviously the air particles are more spread out. And if the air particles are more spread out, the pressure tends to be lower. Whereas if you got a region of compression, okay, so it's really more packed together, okay, or more compressed together. So obviously if the particles are more compact together, are more packed together in a sense, so this would actually mean that, oh, this will cause a region of higher pressure. Okay, so this is a little description on how the series of compression and rarefaction is formed. Okay, so you can take a look at it, and this is the diagram, okay, in terms of showing how the air particles are spread or compact together. So it's quite cool if you think about it. Okay, so I'd like to highlight one thing here, and that is don't be afraid of all these long descriptions. Okay, generally to try to remember them is actually to write them up. Okay, the more you write them, the more familiar you are with them, the better you will get at it. Okay, so that's for this. Now, so obviously because this is wave, you can't run away from graphs. Okay, so I'd like to highlight that in terms of a sound, in terms of sound waves, the graph that they will cover is actually a pressure distance graph. Okay, and there's another type of displacement distance graph. That one we'll cover later on. So first thing, pressure distance graph. So this obviously measures the pressure to the distance. Okay, I say again, this one obviously measures the pressure on the y-axis, the distance on the x-axis. So normally it's y in front, x behind. Okay, so this is a sound wave being generated. So how does the pressure distance graph look? So based on exactly So this is the start point. This is the end point. Okay, let's say end point is here. So what's going to happen is that the further away, so this part corresponds with this part. This part corresponds with this part. Okay, so I'm just drawing this line here to show you. Okay, where all the different regions are actually sort of at. So if you look at it, compression here, refraction here, compression, refraction, compression, refraction, compression here. Okay, and refraction here. So based on this compression refraction identification, what you realize that high pressure, or when the graph is at a high point, is a compression. Low pressure, very low pressure. So when the graph is at the low point, you get your refraction. So in terms of compression refraction, okay, in terms of air pressure, how to look at the graph here, you will need to just take note that the highest pressure, of course, will correspond to the compression. The lowest pressure point will obviously correspond to the refraction. It's really because of the definition that we've covered over here. Okay, so do take note of that. Okay, let's go back down. So I don't think this graph is difficult. It's just that maybe some of you are not so familiar with it yet. So my suggestion, yes, do read up a little bit. Okay, do read up a little bit. And of course, read out all these little details here. Now, but one point to highlight is this. So I want to draw attention to this. The wavelength is the distance. So actually from this graph, you can determine the wavelength. So it's either from one compression to the next. So I'm going to use pink color to show you. So it could be from here to here. This is one wavelength. It can be from one trough to another trough. That's another wavelength. Okay, so sorry, one refraction to another refraction. So that's another wavelength. So just take note of how you can get the wavelength from the graph like this. Okay, next one. This is the one that is a little bit trickier in terms of understanding. Okay, now I want you to look at all these lines over here. Okay, this is where all this line corresponds to the position of the air particles when they are at their rest position. So this is when all particles are at rest. Okay, are at rest position. Okay, now when the sound waves travel, okay, it's going to cause the air particles to move. So comparing this to this, you can see this is the change. Okay, for this particle here, this particle moves slightly in front, this particle moves a bit in front, this particle never moves. So I want you to look at this part. So if this particle has moved the greatest distance, we take it as it has a highest displacement. Next one, somewhere in the middle here, medium. This particle move a little bit. Move a little bit. Okay, sorry, move a little bit. So you can see there's a drop. Move even lesser. Drop even more. Until here. Okay, so this one actually measures this arrow. So the longer the arrow, the higher the displacement. Okay, the shorter the arrow, the shorter the displacement. Okay, so obviously this is not drawn very to scale, but I think you sort of like get the idea. Okay, so you will sort of get the idea lah. Now, and if you look at this part here, this actually corresponds with a region of compression. Okay. Okay, I try to talk louder in case some of you can't hear. So, yeah. Okay, so let me move closer a bit. Okay, now let's continue a bit. So with regard to the whole compression refraction, so you can see here, moving towards the right is positive, and hence this case here, because this displacement moving towards the left would mean it's negative. So this is, let's use a different color. Let's use yellow. Let's use this light green. A bit, a little bit more, quite a fair bit. So obviously at this point, it's the lowest point here. This point, the displacement is a little bit lesser, this one a little bit lesser. So this is how this whole displacement distance graph looks. I want to show you this, do take note, okay. Look at the place where there's compression, look at the place where there's reflection. What you realize that, how come the compression and reflection all at the rest point one? This part is the part where it's a little bit tough, okay. You need to understand that if positive means right, so what you can do is, if positive means right, means the particles here have gone towards the right. If negative means left, all these particles have gone towards the left. So you can see here, okay, for this region, the particles are closing in here. Therefore, that's why this is compression. Now, if I look at this part here, the particles there are going to the left, the particles here are going to the right. So you can see for this particle point, this point here, the particles are going further away from it. So this is a refraction because they are more spread out. So that's one way you can try to interpret this. Okay, but do take note, the compression is not here, refraction is not here. Instead, for displacement distance graph, the compression is actually at the rest point, the refraction is actually at the rest point. You need to decipher what this line means. You need to decipher, need to understand what this whole line means. Okay, so this is a bit more difficult. Has it come out in the exams before? Generally for pure, more often. For combined science, what you typically see is more along of this kind of graph. Okay, so this is more for combined science. Okay, this one is more for pure. But has it come out for combined? For this one, answer is yes. So you still need to know it, okay, because it's part of the syllabus. Okay, so these are some of the other details for you to take a look. Alright, okay, so do read through if you need a bit more examples to further understand this. Okay, now next part, we're gonna go 13.2. About 13.2, what's the key idea? Is that sound needs a medium for transmission, which means that it cannot travel in vacuum. So yeah, it cannot travel in vacuum. So you can see the contrast between sound versus EM waves here. So sound needs a medium to for transmission, which means that it cannot travel in vacuum. Okay, next you need to know how the speed of sound differs in solid, liquids, and gases. So we're going to go into that also. So this one here is just a little experiment called the electric bell sound experiment, which tries to explain and show you how come, to show you that sound cannot travel in vacuum. Okay, so this is quite an interesting experiment. Yeah. In terms of the medium of transmission, do take note, sound actually travels fastest in solid, so it's a bit unique in this case here. So sound travels faster in solid, then it travels slowest in gas. Few of the sound speed that you need to know. So air, about 300. Okay, this one very common question that have to be tested, so you know that it's about 300. Generally, calculation may sometimes lead you to 333 or 330, but the idea is about 300. Okay, that's the speed of sound in air. Okay, now in terms of water and iron, do you need to memorize? No, you don't need. So this is actually just to show you that, yeah, sound actually travels slowest in air. It's actually traveling quite fast in water, traveling even faster in iron, which is a solid. So gas, liquid, solid. Okay, so in summary, what we cover in 13.2 is that sound is produced by vibrating sources placed in a medium. And because it needs a medium, because it must be placed in a medium, so it requires a medium for transmission. So these two sort of like linked up. Okay. Second part, we learned that sound wave is a longitudinal wave. It consists of compression and refraction. Okay. So this is sort of like a description of what sound waves are. And last one, in terms of the speed of transmission, in terms of how fast sound travels, it is fastest in solid, but slowest in gas. Now, the explanation of why is it the fastest is really because solids are very closely packed. So it's very easy for the particles to collide into the next particle, to collide into the next particle, to collide into the next particle. It's a very fast and efficient method, okay, in terms of the transmission, right? So that is for the key ideas in 13.1 and 13.2. Last part for sound is really we're going to concept of echo. Okay, so echo, what exactly is echo? So we're going to learn how echo is formed. We're going to learn how echoes are used to measure distance. So in terms of explaining it, so they typically like to give this example. Ask you to stand in front of a wall, got nothing in between, you clap. What you're going to hear is that the sound will come back to you. This sound being reflected is actually echo. Okay? So the echo is the repetition of a sound. That means if I say ah, later you hear back the same ah, it means it's a repetition of a sound. And how does this occur is because of the reflection of sound. Okay, so echo is the repetition of a sound due to the reflection. Okay? So all this, I won't go through too much. Okay, do read through. The main one I would like to highlight is the echo, uses of echo. So echo can be used to measure distance, long distances. Echo can also be used to detect the object, echolocation. Okay, so let's look at this first one here. So the depth of the sound, depth of the sea. So how can a ship use to detect the depth of the sea? So what they have is that they have a sound generator here. So it sends sound downwards. Then when it hits the sound bed, it gets reflected back up. So signal down, reflected, come back up. So if I'm able to find out how long it takes for the sound to go down and come up, and I know how fast sound travels in water, I'm able to find the distance. Okay, so sounds familiar? Yeah, what we are doing is actually applying the DST triangle. Okay, but do take note, because the sound go down and sound come up, generally the distance that you're always measuring is always 2 times the distance. Okay, sound go down, sound come up, that's why it's 2 times the depth. Okay, but of course you write this, it's even weird lah. Most of you are like, hey, what does it mean? So we stick with D equals to speed times time. Okay, so let's some work example. Let's look at some work example. So a man's standing away a distance D away from the cliff. He lets out a shout, he hears his echo 4 seconds later. How far away is he from the cliff? So the sound went there and come back. This whole duration takes 4 seconds. So what they use is V equals to 2D over T. Then they find it. My method, what I'll normally do is I'll first find the distance equals to speed times time. So the distance I'm measuring is the distance of the sound traveling. Okay, so this distance is actually the distance traveled by sound. So the speed is 330, the time taken is 4. So it will be 1320 meters. Now sound traveled to the wall and come back. But what they want from me is how far is he away from the cliff. So this, what must I do with this? I need to take, so the distance of man to cliff is actually equals to 1320 divided by 2, because it's 2 times, okay? Going to the wall and then coming back. So what you're going to get is 660 meters. So typically I will advocate, okay, do this instead of V equals to 2D over T, because this one is really by understanding what the situation is. However, I know some of you has been memorizing this and applying it correctly, so you can also go ahead and continue to do it. Okay, so many more other examples in terms of using the idea of echo to detect sound. So echo, okay, so key idea. So a lot of examples here. I think in your worksheets, I think in also TYS, you realize that this calculation of distance using sound is quite a common thing that you see. So do make sure you know how to do such a calculation. So as a wrap up for this 13.3, first thing we learned is that echo is a repetition of a sound due to reflection of it. Next thing, what is echo commonly used? It's used to measure distance. It can also be used to locate objects. So That's for 13.3. The last part is actually 13.4. We talk about pitch, we talk about loudness. Okay, so how is pitch and loudness of sound related to the things we are learning about waves? So what do we know? Pitch is related to the frequency of a sound. So we know high pitch is like low pitch like okay, so high pitch, low pitch is linked to high frequency, low frequency. So high pitch actually also means high frequency. Low pitch also means low frequency. Okay, so do take note of this. Next, we're gonna look at in terms of the how to measure all this. Okay, they actually got sort of like a little thing called the oscilloscope, which is here. Then they'll detect a microphone to go and detect the sound wave to observe the sound form. Okay, what I'm going to do is look at here. Now, this is a displacement time graph, displacement time graph. So what it means is that I can actually find out the period and frequency of a wave using this. So first up, let's look at these two. Which one will have the question will be which one has a higher pitch? Okay, let's say I ask you which one has a higher pitch. Let's go to the idea of frequency. If higher pitch means higher frequency, or if higher pitch means also higher frequency actually means more waves in a shorter time. Okay, more waves in a shorter time. So assuming that from here to here and from here to here is the same amount of time. Okay, let's say maybe 10 seconds. 10 seconds. Then it's quite obvious which one has a higher frequency, because in 10 seconds I only got about 1.5 wave or 1 3/4 wave. This one I have quite a few, at least 2 waves or even 3 waves. So 1.5 wave or 1 3/4 wave versus 3 waves, obviously you can see that this one has a higher frequency. Okay, so being able to see from the graph is important. Okay, knowing which one has a higher pitch / higher frequency. So key idea, more waves in a shorter time, this would also mean higher frequency. So that's about pitch. Next, we're going to go in terms of loudness. So loudness is actually linked to the amplitude of a sound wave. So loudness also can think of the volume. So very loud would also means high amplitude of a wave. Soft would actually also means low, okay, low amplitude. So comparing these two, you can see here the amplitude is the displacement right from the rest position, this versus this. So you can see this high amplitude, this low amplitude. Therefore, this sound is louder, this sound will be softer. Okay? So look at all this. Okay, you can see in real life, obviously the sound looks very, very crazy. Okay, but what we normally do in the exam for you is we look at sound in terms of this kind of simple waves. Okay, not such complex waves, so don't worry. So in 13.4, key idea, we learned that pitch is a property that's related to the frequency of a wave. Loudness is linked to the amplitude of the wave. So this is the end for sound and EM wave.